All right, I just wanted to post a very quick video with something that might be helpful if folks are using the Morse oscillator model for their vibrational structure. So if that is the case, there are analytic eigenfunctions for the Morse oscillator model, although they are a little bit complicated. But I found and modified this Python class called Morse, which defines the eigenfunctions and the potential. And I just made a couple of really quick modifications to it so that it would output the potential and the eigenfunctions normalized in atomic units, which is something that you would need. So I've uploaded this class to a Google Drive folder that you will all have access to called Morse Helper code. So that's within the 5200 Google Drive. And then I also have this example Jupyter notebook showing how to use it. So I'm going to walk through that just really quickly. So you have to import the Morse class from Morse. So the file is morse.py. And so the syntax you'll use is say from lowercase Morse, because that's the name of the Python file, import uppercase Morse, because that's the name of the class. I don't actually think you need this. This was something from before, but it doesn't hurt and to also import this fact. This is a conversion factor that I have not used, so it's probably not necessary. Okay, so then the next thing that you have to do is define some parameters for your Morse oscillator. Okay, those parameters will include the masses. So I've put in the mass of hydrogen and the mass of fluorine. It's going to expect that you input those masses in atomic mass units. So those are sort of the simple units that you would get if you looked at the periodic table, right? You would get the mass of each element in atomic mass units. And so for hydrogen, that is 1 atomic mass unit. Fluorine's approximately 19. Okay. Next thing you have to input is the equilibrium bond length of your molecule. I'm doing that in meters. It's going to expect it in meters. So this is what I got from my calculation of the equilibrium bond length of HF. This is just an offset for the potential. So if you had a value of the potential at the equilibrium bond length, I mean, you will from your calculation, and if you want to offset your potential by it, you can set this to that number. You can also leave it at 0. It will not change anything. Okay, next thing is to define your Morse parameters. So these are the fundamental frequency and the anharmonicity times the fundamental frequency in wave numbers. So these you have to extract from your potential from your ab initio calculation, but I just wanted to point out that these are also the numbers that directly correspond to values that are given in the NIST website. And they are actually called exactly these variable names in the NIST website. Well, omega E and omega E chi E. So as close as I can write, it looks like WE at WEXE. So if you wanted to play around with this, if you haven't calculated your Morse parameter values yet and you just want to play around with it, you could use the values from NIST, which are somewhat close to these numbers, but not exactly. These are the actual numbers I calculated for my level of theory. Okay, so those are all the parameters that you need. And then the next thing you do here is actually create a Morse object by calling the Morse class, and it takes those arguments, basically mass of atom 1, mass of atom 2, the fundamental frequency times the anharmonicity, the equilibrium bond length, and then the energy offset, which I've kept at 0. And then it creates an instance of this class. I've just given the name of the instance capital X for no good reason, but that is now an instance of the Morse class, and it has a few different functions associated with it, and also a lot of properties. In the nomenclature of classes, the functions are called methods and the properties are called attributes, but nevertheless, one method is make grid. So I can call x.make underscore rgrid. This is going to make a grid of bond lengths basically from much shorter than equilibrium up to much longer than equilibrium. And then next, x.vMorse is going to call this vMorse method, which is going to compute the Morse potential as defined by these parameters on your grid of bond lengths. And so I'll save them to an attribute, x.v, so that now that's a property of my Morse instance called v, which is the potential. And actually, this will also automatically fill in an attribute called v_au. So this one, x.v, is actually going to be in SI units. So basically, it'll be in joules. And x.r is going to be in SI units as well, which is meters. But when I made the grid, I also added something to make sure that it fills out the grid in atomic units. So here I have now, I can plot the potential in atomic units against the bond length in atomic units, and that's what I have here, right? So the equilibrium bond length in atomic units is, like 1.8-ish or something. So that's what is expected. Okay, now the other thing that's really important, and I'll just briefly talk about this now. So we have these 3 different Hamiltonians. Each one of you are going to be working with a different Hamiltonian. And basically, by solving your anharmonic oscillator model of any kind, you have the matter part basically totally solved. You know the energy eigenvalues and eigenfunctions of these things, right? And I'm using the Morse model, so basically my eigenvalues of p squared over 2m plus v of x, they are the Morse energy eigenvalues, and the eigenfunctions are the Morse energy eigenfunctions. And then I have the bare photon term in each case, and those are just basically the harmonic oscillator states for the photon. Okay, but then I have these coupling terms, and I'm going to need to compute matrix elements because the coupling term, right, for P dot A has the matter momentum dotted into the vector potential for the photon. And then D dot E and Polyphirts have the dipole operator dotted into the vector potential or the electric field. So those are mixed terms. They have a matter term and a light term. So I'm going to have to take matrix elements of these matter operators with my matter eigenstates. And so I need a way to get the eigenstates of my Morse oscillator. So this is what is going on here. I have a method associated with the Morse class called calc_psi_z. And I give it a quantum number, and it will calculate the eigenstate associated with that quantum number. So in this case, I'm just going to show you that I've calculated the ground state, which has quantum number 0, and I'm going to test to make sure it's normalized. So there's a version of that eigenfunction in SI units, which is normalized in SI units. So I'm going to just confirm by integrating its square over my grid of x values in SI units that it integrates to 1, which it does. And then I'm going to do the same thing with the one which is normalized in atomic units. I'm going to integrate it over the grid of atomic units and confirm that it's 1, which it also is. Now I'll plot the eigenfunction for the ground state normalized in atomic units on my grid in atomic units along with the potential in atomic units, and that's the plot here. So this is what the ground state of the Morse oscillator looks like. It looks awfully like the ground state of the harmonic oscillator. Let me just show you a higher excited state just so you can see what the difference is. So this is the third excited state of the Morse oscillator. And one difference is that it has a little bit more amplitude at longer distances compared to shorter distances. And that's because the Morse oscillator rises more gradually at long distances. So there's sort of like less confinement at long bond lengths compared to the harmonic oscillator. All right. So those are the eigenfunctions that we need to be able to compute matrix elements with. And the last sort of important piece of information is that basically both of the matrix elements that you need, either for D.E or Polyphirts or for the P.A Hamiltonian, can actually be written in terms of these matrix elements over the position operator. And so, so there's a relationship here for the momentum matrix elements, which is basically a difference in energies between the Bra state and the Ket state times the imaginary unit times the mass, in this case the reduced mass, times a matrix element with a position operator. And then the dipole integral is basically the charge times an integral over the position operator. So we need a way to be able to compute these position matrix elements, and this is a little function that I added to do that using what we have built in with our class. So we can basically define this function so that it takes an instance of our class, our Morse class in this case, a bra index and a ket index. Then it's going to basically calculate the bra state, calculate the ket state, and then define an integrand, which is the bra state times the position operator times the ket state, and then integrate over the grid and return the value. And so this is just calling that function with your instance, which is called capital X, for ground state as the bra state and first excited state as the ket, and then ground state as the bra, second excited state as the ket, and then printing those values right here. So those are just two different matrix elements over the position, and that's what it gives you. Okay, so that should hopefully provide some assistance to people using the Morse oscillator, but also, you can kind of extrapolate how you would do this with your finite difference eigenstates or your quartic eigenstates obtained from perturbation theory to this procedure as well.